In this lecture, I will study about total solutions of linear recurrence relation with constant coefficients. To get total solution, we must combine the homogeneous solution and the particular solution and determine the undetermined coefficients in the homogeneous solution. Okay, so in order to find the total solution, we must combine the homogeneous solution and the particular solution, and we have to determine the undetermined coefficients in the homogeneous solution. Okay, for a kth order difference equation, the k undetermined coefficients a1, a2 up to ak in the homogeneous solution can be determined by the boundary conditions ar0, ar0 plus 1 and so on up to ar0 plus k minus 1 for any r is equal to 0 or for any r0. Okay, so what is the meaning of this? For a kth order difference equation, we require key boundary condition. Okay, so for kth order difference equation, we require k boundary condition in order to solve the difference equation. So the k boundary conditions are these. Okay, so let us put k is equal to 2. So this is a second order difference equation. For second order difference equation, we require two boundary conditions. So let us put here. So here the last boundary condition is r0 plus k minus 1, that is r0 plus 1. Okay, so here we can write it like this. For second order difference equation, the total number of boundary conditions required are ar0, ar0 plus 1. Why? It is because we have k minus 1 is equal to, we have k is equal to 2 minus 1 is equal to 1. Okay, so we have to go up to ar0, ar0 plus 1. Okay, so for the second order difference equation, we require two boundary conditions, and these are the boundary conditions, and for any r0. Okay, so if let r0 is equal to, let's suppose 2. Okay, then boundary conditions are so put r0 is equal to 2 here, so this is a2 comma a2 plus 1 is a3. Okay, so in this way, if this is a kth order difference equation, then we require k boundary condition. The k boundary condition can be determined by this particular condition. Okay, let the characteristic root of the difference equation are all distinct, then the total solution is of the form. Okay, so this is for the homogeneous solution to this. Okay, and this is the particular solution. Okay, and it is given that let the characteristic root of the difference equation are all distinct. Okay, so the characteristic roots are distinct, then we can have, this is the homogeneous solution, a1 into alpha 1 to the power r up to ak into alpha k to the power r plus pr. This is the particular solution. Okay, so here pr is the particular solution. Okay, so in general we can write the total solution is equal to, this is the homogeneous solution plus this is the particular solution. Okay, come to example 1. So in this example, we'll find the total solution for the difference equation, this, and this is the second order difference equation with right hand side is equal to 442 into 4 to the power r with given boundary conditions a2 is equal to 278 and a3 is equal to 962. Okay, so we have to find the total solution for this difference equation. Okay, so here we can have ar plus 5ar minus 1 plus 6 minus 2 is equal to 42 into 4 to the power r. So let us, this is equation 1. Okay, now we'll first find out the homogeneous solution. Okay, so we'll first write down the characteristic equation, and this is alpha square plus 5 alpha plus 6 is equal to 0. So this is a characteristic equation. Now let us factorize this one and solve this particular characteristic equation. Equal to 0. So 5 alpha can be written as 3 alpha plus 2 alpha. Alpha is taken as common here. 2 is taken as common here. We can have alpha plus 2 into alpha plus 3 is equal to 0. So alpha is equal to, we can have minus 2 comma minus 3. Okay, so the homogeneous solution can be written as H is equal to A1, this is, all the roots are distinct, so A1 into, this one is alpha 1, this one is alpha 2. Okay, so A1 into minus 2 to the power r plus A2 into minus 3 to the power r. Okay, so let me equation number 2. Okay, now we will find this A1 and A2 later on by using these boundary conditions. Okay, so now come to the second is the particular solution. Okay, so see here in the right hand side we have 42 into 4 to the power r. Okay, 4 is beta here, and this is not this beta is not same as any one of the root. Okay, and we have this 42 is a polynomial of degree 0. So the particular solution is of the form P for this 42, this is constant, that is P 4 to the power r. Okay, so let it be 3. Now substitute 3 in 1, we get so here we get P4 to the power r plus 5 P4 to the power r minus 1 plus 6 P4 r to the power minus 2 is equal to 42 into 4 to the power r. Okay, now let us solve this one. This implies we'll get, let us take 4 to the power r common here, so this will be P plus 5 by 4. So this 4 to the power r minus 1 is equal to 4 to the power r divided by 4. It can be written as 5 divided by 4 P plus 6 divided by 16. So 4 to the power r minus 2 is equal to 4 to the power r divided by 16. 4 square, that is 16. So 6 by 16 into 4 to the power r, sorry, here P of right here is equal to right hand side 42 into 4 to the power r. Okay, So we can have and take 16 as LCM here, so it is 16p plus 20p plus 6p into 4 to the power r is equal to 42 into 4 to the power r. This implies we have 42p, okay, numerator divided by 16 into 4 to the power r is equal to 42 into 4 to the power r. Okay, so comparing left hand side with right hand side, we get 42p by 16 is equal to 42, which implies p is equal to 16. So this is the value of p we got here. Okay, so hence ARP, this is the particular solution, is equal to, this is the ARP, this is p, we got the value p is 16 into 4 to the power r. Okay, so this is the particular solution, we got it here. Okay, now we'll find out the total solution. Okay, so total solution can be written as AR is equal to ARH plus ARP. Okay, so this implies AR is equal to ARH is nothing but A1 minus 2 to the power r plus A2 minus 3 to the power r plus the particular solution is 16 into 4 to the power r. Okay, so let me question 4. I will put the boundary condition. So put A2 is equal to 278. Okay, that is r is equal to 2. So this is the value of r in 4. So we get, so put the value of r is equal to 2 here in this equation 4. So we have A2 is equal to A1 minus 2 to the power 2 plus A2 minus 3 to the power 2 plus 16 into 4 square. This implies we have A2 is equal to 278. Okay, so minus 2 square is equal to 4 A1 plus this one is 9 A2 plus this one is 256. 16 into 16 is 256. Okay, so it can be written as 4A1 plus 9A2 is equal to, take this constant at one side, so we'll get 278 minus 256 is equal to 22. Okay, so let it be equation number 5. Okay, similarly put A3 is equal to 962, that is r is equal to 3 in 4, yet A3 is equal to A1 minus 2 to the power 3 plus A2 minus 3 to the power 3 plus 16 into 4 cube. This implies A3 is nothing but 962 is equal to minus 2 to the power 3 is minus 8, so this one is minus 8 A1, this one is minus 27 A2 plus this is equal to 1024. Okay, So which implies it can be written as minus 8a1 minus 27a2 is equal to, so this will be 962 minus 1024 is minus 62, which can be written as 8a1 plus 27a2 is equal to 62. Let it be equation 6. Okay. Now solving 5 and 6, we have, so to solve 5 and 6 we have, so write down the equation first. 4a1 plus 9a2, this is equation 5, is equal to 22. This one is 8a1 plus 27a2 is equal to 62. Okay, so let us multiply the equation 5 with 2. Okay. And subtract this one, so we cancel out. This one is 18a2 minus 27a2 is equal to minus 9a2 is equal to, this one is 44 minus 62 is equal to minus 18. This implies a2 is equal to 2. This is the value of a2 we got. Okay, we put the value of a2 in equation 5, so we get 4a1 plus, this is 9 into 2, that is the value of a2 is equal to 22. This implies 4a1 plus 18 is equal to 22. This implies 4a1 is equal to 22 minus 18 is equal to 4. This implies a1 is equal to 1. Okay, so this is the value of a1 we got. Okay, so now put a1 and a2 in 4. This is the total solution. Okay, we get, so we get AR sorry AR is equal to, we have a1 into minus 2 to the power r plus a2 into minus 3 to the power r plus 16 into 4 to the power r. Okay, so AR can be written as, the value of a1 is 1, so this is minus 2 to the power r plus value of a2 is 2 minus plus 2 minus 3 to the power r plus 16 into 4 to the power r. Okay, so this is the total solution we got, and this is the answer. Okay, come to example 2. Here we will find the solution for the difference equation, which is the order of 2, and in the right hand side we have the constant 4, and here r greater than or equal to 2 with given boundary conditions a0 is equal to 1 and a1 is equal to 3. Okay, so let us write down the difference equation first. So this is AR minus 5 AR minus 1 plus 6 AR minus 2 is equal to 4. So let it be equation 1. First of all, we will find out the homogeneous solution. Okay, so the characteristic equation is alpha square minus 5 alpha plus 6 is equal to 0. So this is the characteristic equation. So let us factorize this left hand side. So we'll get alpha square minus 2 alpha minus 3 alpha plus 6 is equal to 0. Okay, so take alpha as common here. Minus 3 is common. So it can be written as alpha minus 2 into alpha minus 3 is equal to 0. This implies alpha is equal to 2 comma 3. Okay, so we have distinct roots 2 and 3. So the homogeneous solution can be written as is equal to a1 into 2 to the power r plus a2 into 3 to the power r. So let it be equation number 2. Okay. Now we'll find out the particular solution. Okay. So we have constant at the right hand side. So particular solution of the form P. Okay. So substitute P in 1. We get P minus 5P plus 6P is equal to 4, which implies 2P is equal to 4. Sorry. So we have, which implies P is equal to 2 here. Okay. So the particular solution ARP is equal to 2. So this is equation number 3. Okay. Now we'll find out the total solution. Okay, we know the total solution is AR is equal to ARP plus H, which implies AR is equal to AR. Okay, so ARH is A1 into 2 to the power R plus A2 into 3 to the power R plus the particular solution is 2. Okay, so let me write down H here first. Then P. Okay, so this is the homogeneous solution, this is the particular solution. So let it be equation number 4. Okay. Now we have boundary conditions. So given a0 is equal to 1, so that is put r is equal to 0 in 4, we get, so we get a0 is equal to a1 to the power 0 plus a2 into 3 to the power 0 plus 2. So we have value of a1 is equal to 1, and this is a1 plus a2 plus 2, which implies a1 plus a2 is equal to minus 1. Okay, so let it be equation number 5. Again we have given a1 is equal to 3, that is put r is equal to 1 and 4, we get a1 is equal to a1 into the power 1 plus a2 into 3 to the power 1 plus 2, which implies a1 is equal to 3. This one is 2a1 plus 3a2 plus 2, which can be written as 2a1 plus 3a2 is equal to 3 minus 2 is 1. This one is 6. Okay, so solving 5 and 6, so you can have equation 5 is a1 plus 2 is equal to minus 1, 2a1 plus 3a2 is equal to 1. This is equation 6. So let us solve this one. So let us multiply the first equation with 2. So we cancel out 2a2 minus 3a2 is equal to minus a2 minus 2 minus 2 minus 1 is equal to minus 3. So we have a2 is equal to 3. Okay, now find the value of a1. So put the value of a2 here. So we'll get a1 plus 3 is equal to minus 1. This implies a1 is equal to minus 4. Okay, put a1 and a2 in equation 4. So we'll get equation 4 is nothing but ar is equal to a1 into 2 to the power r plus a2 into 3 to the power r plus 2. This implies ar is equal to, so we got the value of a1 as minus 4 to the power r plus value of a2 is 3. So this is 3 into 3 to the power r plus 2. Okay, so this is equal to ar is equal to 4 is 2 square. Okay, so this will give 2 minus 2 to the power r plus 2 plus 3 power 1. Okay, so this is the answer.